All right. Welcome back, everyone, to day 3 of What's a Microcontroller with Python and the Microbit. Today, again, it'll be me, Andy Lindsay, Ari Alvarez, and Stephanie Lindsay will be on the chat, and Stephanie will be chiming in to if you chat questions that she thinks are worth discussing as a group, as opposed to sometimes it's just a quick chat reply and you're on the way. So so thank you, Stephanie, for keeping an eye on everything, and Ari as well. So today we are going to test run some tests, and then just see some applications for the servo and the potentiometer that you built during the homework. And after that, we'll talk about some of the upcoming activities and projects that we'd like to add to the bookshelf of chapters that we've been working from. And then we'll talk about purchasing student resources, teaching resources, and then additional resources like the cyber.org curricula. We'll also talk a little bit about some other microbit kits that you might find to be kind of interesting, including the Cyberbot robot. Okay, so the homework was simply to attach or connect this potentiometer circuit here, and then this servo circuit right up here. And before we connect the batteries, I would like to just basically have all of you take one final look at both of these circuits. So I'm going to try to zoom in here. So let's first take a look at the potentiometer circuit. So everybody look at your board and look at the screen and make sure that the lowest black wire in the lower right is going from a socket by the blue column to J30. The red wire above it should be going to a socket by the red in the red column by the red line to J28. We want to have and of course, you can plug into basically any particular socket on the same row, and the effect will be the same for these two wire ends right here. And likewise, you could go up or down here, but you want to make sure that you're still in the red column and in the blue column for the black wire. And then we want the potentiometer sharing the two pins coming out of the potentiometer, one here and one here, sharing the same row with row 30 and row 28. Then on the other end, there's a single pin, and that's going to be in row 29. And then also in row 29 is a red-brown resistor that goes to row 26, or the same row as the P4 pin on the edge adapter. So everybody double check those items, please. Ask me if you want me to call out any of that. Okay, I'm seeing everybody looking up. Are we good to continue to the next checkup? Nods.
Sorry, Andy, just one question here.
Yes, go ahead.
The potentiometer is a little bit, quite a bit high. I couldn't press it in very much. I'm not sure if it's making proper contact. Is that normal that it's high like that?
Let me think about that. Mine is definitely a little high too. And the reason for that is because the pins flare at a certain point. So you most likely got each pin to sink in 1/4 of an inch of the way.
Okay, and it looks like it's about I don't know, less than 1/4 inch above it, not quite 1/4 inch, but it is, seems like it's floating pretty high. I was expecting I could push it in more, like the buttons go all the way down in there, but the potentiometer really sticks up a lot. So I guess that's normal.
That's a really good question. I had not noticed that, but you're You're very right. Let me get to the webcam here. All right, so looking at that, it is pretty high up.
Okay,
Zoom
I
in
guess we'll
just a little
see if
bit.
it works then when we try it out, but yeah, appreciate you
Yeah.
checking that. Let me know. Thank you.
Oh, certainly. Okay. Next up is the servo circuit. So that is mainly right here. I'm going to focus on the wiring. Okay, so that's a pretty good view of the servo circuit. So the plug should be going over a 3-pin header. So there should be a 3-pin header in B2, 3, and 4. And then this plug should be going over it. And it should slip nicely down over the 3 pins that are still sticking up. Then we want to make sure that A5 has a black wire going to a socket by the blue line. And A4 has a red wire going to a socket by the red line. And then A3 should have a 220 ohm resistor, that's red, red, brown color code, that on its other end connects to the same row as the P16 pin on the edge adapter. So please double check those.
Andy, is it possible to see a blow up of your connection?
Yeah, I'll try. Let's see here. Gotta get that cable out of the way somehow. There, and then see if we can bring it into focus just a little bit better. Okay, I think that's as good as it gets. How's that look?
Could you take your pencil and point to one of the colors?
One of the colors. Okay. So here is a red plus. This is the red column. Here is the blue minus. This is the blue column. This is the black wire going from the blue column to P5. This is the red wire going from the red column to P4, or I'm sorry, to row 4. So I'm sorry, row 5, black wire to column by blue line. Red wire going from row 4 to column by red line. And then here is the red, red, brown, and gold on the resistor that's going from row 4 to P16.
Row 4 or row 3?
Row 3, pardon me, and thank you. Row 3, the resistor is going into row 3, D3, in my case, to the same row as P16 on the adapter. I can't tell, is that row 14? See if we can take a peek behind the resistor there. Yeah, it looks like row 14 is where the P16 pin is plugged into on the resistor there. Okay, good enough. Excellent. All right.
What color resistor?
Oh, the resistor color code is red, red, brown, gold. Red, red, brown, gold. Okay, are we ready to move on? Have we double checked our circuits? Okay, excellent. Well, let's have some fun then. And after a little bit of fun, I'll try to loop back and show you the more methodical approach that the students end up following when they're working through this in a lab or classroom setting. So starting with servo position control, I'm going to skip to connect and test the servo because we all were really careful about how we connected it. And so let's see here. Now I'm getting a little bit ahead of myself, so I'm not going to paste this link in just yet. There's one final detail, which is now that we've double checked our connections, need to zoom out. Now that we've double checked our connections, let's go ahead and add those batteries to this battery pack, which should be plugged in with the red wire on the left. As you're looking at the plug where it goes into the edge adapter. Okay, so here go the batteries. Make sure to do the flat end against the spring and the end with the bump on it against the other part that doesn't have a spring. And then slide the lid on. And then we've got our servo batteries. Okay, are we ready? Thumbs up, thumbs down. Awesome. Okay. Now, now that we've got the batteries in, let's go ahead and try what this script is going to do is it's going to make that servo horn turn to 4 different positions. It'll start at 0 degrees, then it'll go to 45 degrees, then 90 degrees, then 180 degrees, and then start over I'll play it one more time through 0, 45, 90, and 180. Okay, and so now we need to go to the connect and test script. Go ahead and paste this into you. All right, check your Zoom chat.
When we plug the battery in, should anything have happened on the board? Should the light have come on from microbit?
Let me think about that.
Because I only have the battery pack plugged in now. I don't have my cable plugged in.
Okay, thank you. That I guess I got ahead of myself here. Yeah, we also want to plug in the microbit cable. All right, and then pasting from the chat over whatever is in your python.microbit.org editor. Then connect, select your microbit, approve the connection, click flash. And then let's check our servos. So right now there was 0 degrees, there is 45 degrees, 90. By the way, it's going to be a rough approximation, and it depends on also how you have the horn attached. But there is 0 degrees, 45, 90, and 180.
Andy, could you put the copy and paste the link to that Learn page that you're on into the
Yes,
chat?
it's on its
That-
way.
That will help folks who are having trouble copying and pasting from the chat window, or who just joined us and need to know to
Where we
back,
ended up.
yeah, to back up a bit and look at the connections. Thank you.
Excuse me. I'm sorry.
Yeah, go
Andy,
ahead.
I noticed that it does, it looks like it's doing 3 counterclockwise moves and then 1 clockwise move. Is that normal then, or is there something wrong?
It may be that, why not, let's see, let me think this through. I'm going to bring the webcam back up, or the document camera. Okay, so you're saying it makes 3 counterclockwise moves?
And then it does 1 clockwise.
Yeah, so it's basically only going back to roughly 45 degrees. So that's 0. So what it's doing probably is going back to there. Now that's going to depend, of course, on how you have your horn pushed onto the output shaft. So one thing that might indicate is,
Oh, yours seems to be doing the same thing though, right? Yours is going 1,
oh, okay.
2, 3. The third one's coming up.
Yeah, and then
And
it
then it's
goes all
gonna
the
go-
way back.
Then it goes clockwise from there. So 3 counterclockwise is in 1 clockwise move. I don't know. This is like a shortcut to that degree angle that instead of going in the same direction, it looks like it's shortcutting it to get back to 180.
Yeah, so the reason for that, can you see the code to the right of the servo?
The
So-
code to the right of the servo.
Oh,
You
on
know,
the,
servo itself then?
on my screen. If you go over to my screen, you'll see
Mhm.
some code to the right of the, so I've got the servo on the left side of my screen, and then
Mhm.
I've got the script on the right
Oh, okay, I
side of my
see.
screen.
Right, I see the script.
Okay, so with the script, what it starts out doing is saying 26 is the magic number for 0 degrees. Then 51 is the magic number for 45 degrees. And so what it does is it uses this pin 16.write analog signal. And I'll come back around to why that magic number and a couple other things. So here we have a statement that tells the it tells the microbit to send the signal to the servo that makes it move its output shaft to its 0 degree position. Then sleep 4000 makes it stay there for 4 seconds. After that, we make it move to 45 degrees for another 4 seconds, then 90 degrees for another 4 seconds, then 180 degrees for another 4 seconds. And at that point, what happens is this while true loop goes back to the beginning. And when it does that, the servo horn turns all the way back to 0 degrees. And so that is what the counterclockwise motion is. So these are position statements. These are statements that tell the servo, hey, servo, hold the position that corresponds with the number 26, which happens to be 0 degrees. Hold the position that corresponds to the number 51, which happens to correspond to 45 degrees. And I have also a helpful little graphic for that.
So they're absolute positions because it can't wrap around. It's always going to go. If you go to a lower number, it's always going to go clockwise, correct?
Well, so it's going to turn whatever direction it needs to turn to get to the position, to the angular position. So a standard servo is the kind of motor that controls a boat rudder in your radio controlled hobby boat. It might control the steering in a radio controlled car. It might control the various flaps in a radio controlled airplane. And in all three of those applications, what the servo's job is to receive a signal that tells it where to position itself. And then it faithfully positions that boat rudder, that car steering, that airplane flap. And so each of these tells it to turn to a position, and then it holds that position for 4 seconds for each one. So we're not expecting it to spin, although there is a kind of continuous rotation, that there is a continuous rotation version of this that will spin. And there's a slightly different set of rules for what numbers you use to make it spin certain speeds and directions. Is that okay for an answer?
Yes, thank you very much.
Certainly, yes. So as you're looking at the servo, the idea is that it's going to be holding a position for 4 seconds, each of its positions for 4 seconds. So one of the things that we have the student do is add in the 135 degrees by figuring out that they want to go halfway between 77 and 128 to get to that new position. There are some equations that you can actually solve to figure out if you know, for example, that the number 26 results in 0 degrees and the number 128 results in 180 degrees. we can revisit the two equations in two unknowns that is introduced in algebra class. And we can actually say, okay, 25.6 gives us 25.6 for y1 gives us 0 degrees. 128 for y2 gives us an x2 of 180 degrees. And then I'm going to leave the step-by-step to you, but basically there's the solving for m and b in a y equals mx plus b equation. And so we start with these numbers and then go all the way through to say, okay, m is 56.9, 56.89, pardon me. And then b earlier was 25.6. And so I like doing this, although later on, we actually just use a function, a Python function that solves for y equals mx plus b. But this is, I believe, the second or third time in the chapters where we by hand solve for y equals mx plus b to figure out a relationship so that we know what numbers we need to plug into the Python script to make the circuit behave a certain way. And in this case, that's the servo. Let's try push button servo control. Let's see. Stephanie, should I still be pasting in the address first?
I think pasting in the address is helpful.
Okay.
And then pasting in the code.
Okay, so here is the address of the page we're at and some code that will do nothing when you run it. But if you press and hold one of the push buttons, you'll see that the servo will rotate toward in a particular direction. The upper push button, I believe, is going to be counterclockwise, and then the lower push button is going to be clockwise. So on the screen, if I press and hold the lower push button, the servo turns clockwise until it reaches its 0 degree position where it can't go any further. And then if I press the upper push button and hold it, the servo turns until it reaches the counterclockwise limit. And then you can press the button for a little while to cause it to go to other positions. It's kind of a neat little script. A reminder that if something isn't working and I moved on too soon, you can feel free to unmute yourself and say, can I have another 30 seconds or whatever you think it's going to be? Yeah, I see a hand up, Robert.
My servo is not working and it's getting really hot.
unplug it.
Ooh.
Oh, almost too hot to touch. I did.
Okay.
Hmm.
I couldn't even touch it. It smells like it was melting. I don't know.
Yeah, so let's let it cool off a little bit. Here, I'm gonna unmute. Can you, or unscreen share? Can you put your board up to the screen and let's see what you got. See if I can. Yeah, I'm looking for where the servos connect. Can you go up just a bit?
About there.
Okay. I'm seeing the lower part of your board. There we go. Okay, so are the two wires that are going to, okay, so the black wire is going to the blue column. It looks like the red wire is going to the,
It's going to the red column.
yeah. Okay.
When I plugged the battery pack in initially, absolutely nothing happened. Is
Yeah.
there something supposed to happen when I did that?
Oh, absolutely.
When I plugged it in, nothing. And now
Yeah.
my servo is like red hot. I'm
Okay.
pretty sure all my connections are solid. Okay, you know, I'll just follow along. But
Yeah, I'm terribly sorry about that. We can send you a new servo. If it turns out, let's
it might be
reconvene.
this. Okay, it might be
Robert-
the board itself. But okay.
Yeah, Robert, will you have a little bit of time after the workshop
Yes.
today? Okay,
Yes, I
good,
will.
good. So we can do a little troubleshooting session then.
Okay, continue
right.
on. Thank
Everybody
you.
else ready to go? Are we all good? Okay. All right, so next up, let's take a quick look at what the students do as opposed to just the educators or the workshop version of this. So the students actually start out by selecting, by seeing the servo and learning the names of the different parts of the servo, and then grabbing the servo and the servo horn, and then doing that little procedure of putting the horn on, rotating it clockwise, taking the horn back off, and then attaching it so that it's pointing to the right for 0 degrees. Then they go through the steps of building the circuit and carefully looking at the circuit to make sure that there aren't any incorrect connections. And then after that, this is just take one last look before we go to the next page. Then the script that they run is, oh, pardon me. I apologize. I meant to go here because they start by grabbing their battery pack.
I don't think you have your
Andy,
screen shared.
You're not. ready.
Oh. Okay, so I'm going to start over. So, so the students actually start out by checking to see what they've got from their previous tutorials, because some classes will jump straight to a chapter and some students will jump straight to a chapter. And so there's the first section is the setup from the previous tutorials. So this was LED lights and then push buttons. And so we left all those connected. And so that's what we start with. Then the students find their battery pack. And they also set up a circuit to measure voltage. So what they do is they take the measure volts that they attach the clips to the 3-pin headers in the same way that we did when we were measuring volts on the first day. And then they plug in the red lead to the column on the left, far left, the red sockets, or the sockets by the red stripe. And then the column next to it are the sockets by the blue stripe. And they plug the black probe in there. And that is setting up to measure voltage. Then they open script and tests and download measurevolts.hex. And I'll go ahead and paste this page in for anybody who, I'm mainly demoing this, so I'm not gonna spend a lot of time on it. So it might be better to watch, but I will paste the links in anyways. Paste. Enter. Okay, so this is a case where you have to right click measurevolts.hex and select save link as, and then click save, and it should end up in your downloads. Okay, then the students go ahead and drag that that hex file and drop it into their online python.microbit.org editor, and then flash it. And in this case, we're using the terminal as opposed to the Cyberscope. So, so we'll go ahead and open the terminal.
We do have a question at this point. In the
Okay.
editor, should we save as Python script or as a hex file?
Always hex files. So whenever you're saving, load save, download project hex.
Why is that?
So that was discussed on Monday and again on Wednesday. The reason for that is because, one, when you click download Python script, you get a warning saying, are you really sure you want to download the Python script only? And sure, we can click OK and choose to keep it. That was the other thing, is that your Chrome browser will tell you, hey, it's a Python script. That could be something malicious, because Python scripts have been in the past used for nefarious purposes. People would unknowingly download them, and then it would somehow infect their computer, possibly. So second reason, this message, there's a message comes up, says, hey, Python scripts are dangerous. Third reason, from multimeter import. Well, okay, I'm going to.
It just simply, when you download the hex file, it includes the imported objects with it.
Oh, that's the third reason. I'm opening the Python file. I'm reopening the Python file. And when I hit load save, I see that I only have measure volts, but it says from multimeter import here, and there is no multimeter module that's part of the project, because all I did was open the script. Now, if I instead open the hex file version of it, so now I'm dragging and dropping the hex file version of it, then when I hit load save, there are two files in the project. There's the main file, measure volts, and there's multimeter.py.
Okay.
So that is why we always save as a hex file and open hex files.
For reference, the open serial button is also referred to as the terminal.
Yes. Okay, now got to get over to the. All right, so I'll go ahead and connect those. So this is what the students do. They connect the alligator clips to the 3-pin headers, and then they plug in the P0 black lead to a socket by the blue column, and then the P2 red lead to a socket by the red column. And then they see that they get 3.28 volts. Now that's actually the doing of the USB. If I were to unplug USB, I would see a slightly different value. but I wouldn't be able to see it because, because the USB is unplugged. Yeah, that's interesting. I'm wondering why I'm seeing 3.3 volts. I'm gonna have to leave that one for an emailed follow-up. All right, so you can also change this to device equals Cyberscope and then flash it. And then open up the Cyberscope, click connect, select your microbit, and then you'll see the 3.28 volt measurement as it would look in a voltmeter. And I'm really not sure why I'm seeing 3.3 volts. I want to see 3.1 volt. I'm going to have to take a closer look at the, I don't know whether I made a wiring error or what's going on. Anyway, then we talk about how batteries work. And so what they've done is they've basically measured the voltage of the battery pack and made sure that they have the 3.3 volts is fine. It's just I expected to see a little bit less. And then they go to learn about the servo and its parts and go through the putting the horn on so that it's ready to have 0 degrees. Then they do the building the servo port step, double check their work, and then move on to the test that we just ran. Are there any questions before I move on?
There's a comment from Robert. He figured out what was going on with his servo.
What was it, Robert? The armature. Oh,
Put the armature on
interesting.
too tight. Put it on so tight that it couldn't move it.
So it was actually just fighting against itself. That's so unusual. I did not expect to.
I pushed it down probably too hard. And there was so
Okay.
much friction that the motor could not move the armature, and so it was overheating. I
All
took
right.
the armature off, put it back on looser, and it's working fine.
That's really good to know. Thank you for that astute troubleshooting. We
Yeah.
can actually let our techs know about that so that if any calls come in, that can be something to ask.
Yeah, it was just too tight, and the motor was straining and overheating.
Okay. Wow, nice catch. Yeah, we can also think about adding a little troubleshooting blurb to one of these pages too. All right, so there is also tilt control, which is kind of fun. I'm just going to play you the video of it, and maybe we'll go back to this later, but there's a fair amount of material to cover today. So, if you're holding, there's an accelerometer inside the microbit, and the script for servo points up is after you've got it so that you know that pointing to the right is 0 degrees. You can actually hold the servo next to your microbit like this, and as you rotate it, the microbit's display will show you which way is up, and it will also make the servo point in the corresponding direction. So when we rotate it a little bit more, that's the best the microbit can do for pointing up, and then the servo actually does a little bit better job there. And then here is up. And then when you're sideways, we've still got the servo and the display both pointing up. So that's a neat little thing that uses the microbit's built-in accelerometer. And you have to be holding the board vertically like a steering wheel in front of you. You can't just rotate it on the sitting flat on the table and have it work. You have to, point it. Well, let me see. So essentially, here's the table. So you're actually holding it vertically and rotating it to make the servo work. It's a really fun activity. And if possible, we'll loop back around to that, possibly, or possibly do it after the end of the official session. Just wanted to know it's there though, the servo tilt control activity. Okay, next up, I would like to try out the potentiometer and make sure that's working for everybody. Okay, back to normal on the slideshow. So we're jumping straight to the so what this is a draft that has not yet made it to the learn.parallax.com site. And this is an example of measuring the resistances inside the potentiometer. So I mentioned that there was a measure resistance activity inside the electrical measurements chapter on Monday. And so what I want to do first is just make sure that that our application circuit works properly. And that is going to be with this script right here. I'll paste in this chapter. It's a chapter draft. So there is a link to the chapter draft. And then here comes the test code, the test script. Okay. Flash. And then after loading this one, click the open serial button. If you have your Cyberscope running, make sure to disconnect the Cyberscope. If you don't, then no worries. And what you will get is a number that corresponds with the potentiometer's position. So I'll go ahead and set aside the measurement clips. And now, if I rotate the potentiometer, if I rotate it counterclockwise, notice that the value at the bottom of the terminal, the black terminal, starts to increase. And I'm gradually turning it counterclockwise, and I just reached the counterclockwise limit. And I get a number that's somewhat familiar, 1023. That was what we used to make a light shine as brightly as possible on Wednesday. And as I turn it clockwise, you can see that the numbers drop until I get pretty close to 0. That's about 5. So I'd like you all to try that next. Try turning the potentiometer through to it's got about a 270 degree range, or 3/4 of a turn. And so as you turn the knob that's sticking up the top of the potentiometer, you should see these ADC measurements changing. And the further counterclockwise you turn it, the higher the value will get until it hits its little internal limiting stopper. And then as you turn it clockwise, the numbers should go down until you get pretty close to 0. And really all you want to see is pretty close to 1023 and pretty close to 0. So, that might be 1,000 for you, or even 980. And then on the low end, it might be 50, or it might be right on 0. There's some variation in these parts, which is normal. And in order to keep the price of your kit reasonable, we went with a part that had a little more variation to it, which gave it a little less cost.
Mine is the opposite. As it go counterclockwise, it goes down. As it go clockwise, it goes up.
That's interesting.
That's me. Yeah.
Typically that happens when you swap the wire connected to the, let me see if I can zoom here. Okay, see how we've got a red wire connected to the pin that's in row 28?
Yep.
Okay. If I were to revert, and then we've got a black wire connected to the blue column going to row 30. So red wire should be red column on the left going to row 28. Black wire should be in a blue column socket going to 30. And as typically, if those are reversed, so now I have the red wire, or the top, the row 28 wire is connected to the blue column, and the row 30 wire is connected to the red column. And now if I turn it counterclockwise, it's the lowest value.
But you just turned it clockwise, didn't you?
Oh,
If you
you know
turn to the-
what? My Listexia is showing. Yeah, I apologize. I was calling that out completely wrong.
Okay. Sorry.
No, my apologies. Goodness. Yeah, I did not. I was saying that all wrong. So as you turn it to its clockwise limit,
It's higher numbers.
it's high. Yeah.
Okay.
And then when you turn it to its counterclockwise limit, it's low. And unfortunately, when I was writing that in the web page, it went through 2 editors to make sure that stuff like that gets caught.
Andy, have you experienced different browsers giving us different effects?
Okay, so the Chrome browser is the only one that is recommended currently for programming the microbit and using the Cyberscope. I think that Firefox may now support the Cyberscope. I'm not sure. Mileage really varies. This is, for example, this serial terminal, I really don't think it works in Microsoft Edge. And then essentially it's kind of hit and miss depending on the type of browser, how much of Chrome's Web USB and Web Serial are supported. And so the only one that we know supports it fully is Chrome.
Okay.
Great. All right. So here's another fun one. Let's, now that we've got our potentiometer tested, and sorry about the confusion there. let's go ahead and use the potentiometer to control the rotation. And incidentally, there are also activities. So this activity right here is taking the most fundamental measurement. It's taking the raw value that read analog gives back. Pin 4.read analog is measuring the voltage connected to the potentiometer. Let's see. So basically, read analog of 4 is checking the voltage right here. And by twisting the potentiometer knob, it causes the voltage to vary here and also here. I'll show you that in just a minute. But the tutorial also takes the student through, okay, now that you've done the raw value, let's take a look at I think I'm in the wrong spot. Potentiometer controlled servo. Oh, yes, I am in the wrong spot. So we're doing potentiometer lessons. And so okay, so this was, okay, so here we are. So this is the, what we're doing here is saying, hey, yeah, sorry about this. I'm having some technical difficulties. Let me see if I can get to the right spot. Okay, maybe I pasted the wrong thing in here. Trying to figure out if there's a way I can show you. Yeah, I apologize. I don't know how, but I made a mistake with the scripts when I was pasting them into here. And so I don't have a particularly good example of converting to voltage. And then also converting to angle, which is what this chapter is supposed to be doing. Let's see how potentiometer controlled servo is looking.
Excuse me, Andy, I noticed some code there that I was interested in. I've never seen anything like that where it says X is equal to X space Y space Z. You just were on that a little bit before. Is that valid Python code?
I don't know. Let's see if I can.
I thought I saw something there that looked a little unusual, but I just thought I could learn something from it.
These scripts are a little bit scrambled and I don't know what happened.
Oh, okay, so maybe that was just a mistake. It said X is equal, it looked like 3 characters after that. I thought I was doing some type of maybe setting those values equal all 3, like 3 variables equal to another variable all in one line. I wasn't sure what it was doing. I've never seen anything like that at all. Maybe it's valid. I'm not sure.
Yeah, I'm not sure either. Okay, maybe it's in measure potentiometer voltage. Maybe, yeah, this is taking too long. I know at least that potentiometer controlled servo, that code looks see, this is a light intensity one. I don't, oh, that's the potentiometer controlled light. Let's do that one while we're here. Copy. Okay, I'm going to paste this into everybody. Okay, so this is one of them where all it's going to look like on my end is the light is flashing. But for you, it should actually look like brightness control. So when you rotate the potentiometer all the way counterclockwise, the light is either off or very dim. And we can definitely see that this green light is barely glowing. And then as I turn the potentiometer clockwise, the light intensity increases. And so that's putting two things together. That's putting the light brightness from the LED chapter together with the new potentiometer to measure rotation. And so we're converting a rotational position into brightness.
What causes the blinking on your screen?
Oh, the thing that causes the blinking on my screen is that the brightness is actually done using persistence of vision. So the potential or the LED light is actually being flashed on and off rapidly. And when we look at it with our eyes, that registers as a brightness. And the on and off flashing, the more time during that on-off flash that it spends on, the brighter the light looks. The less time, the dimmer the light looks. It always flashes at the same speed, 50 times a second. And it's just how much time is the light on during that 50 times a second. And the flicker in my video screen is simply because it's basically seeing the light and capturing it when it's on, and then when it's off, and then when it's on and when it's off. And the flicker does change a little bit. Okay, so that's dim, and we can see it flickering less, and that's because it's on for less of the time, and the camera catches it on less of the time. Hopefully that makes sense. All right, so then the potentiometer controlled servo. I didn't paste it to you guys, sorry. There you go. So now, when this script is running, it actually, I believe, rotates the opposite direction. The servo horn rotates the opposite direction from how you rotate the adjustment knob on the potentiometer. So I'm twisting it gradually counterclockwise, and it looks like the servo arm is turning clockwise. Then when I reverse and turn the potentiometer clockwise, the servo arm turns counterclockwise. Stephanie, was that visible or was
Yes, it
okay,
was
so I didn't obscure the view or anything?
no.
Okay, good, excellent. And we had to use y equals mx plus b in the lessons to come up with these numbers here, which takes the raw measurement and of the potentiometer and turns it into a range that is useful for the servo. And then here is the one that will actually make it turn the same direction. So this is going to go in a try this section. So the student has to modify the code in order to get this result. There it is in the chat window. Hopefully a screwdriver will view better. So I'm going to turn the screwdriver a little further clockwise and nothing happens, but as I turn it counterclockwise, the armature or horn on the servo follows the motion of the potentiometer now. There's counterclockwise, and there is clockwise. All right, did we all get that running? Thumbs up, thumbs down? Got one thumb up. Two thumbs up, thank you.
Excuse me, Andy, I just wonder if you could review what the code does. I'm not sure what the variables stand for either. I know you probably said it before, but I'm just trying to understand what the code is doing.
Actually, I didn't. I'm kind of skipping through here. And so, this is ADC stands for analog to digital conversion. And that's a value between 0 and 1023 that pin 4.read analog gives us. And again, the potentiometer is connected to pin 4, and it will give a voltage between 0 and 3 volts. And so those things are step-by-step covered earlier on. So I skipped straight to the application stuff. Let's see here. Am I in the right spot yet? So what we do is we start by talking about, okay, a potentiometer has a clockwise and a counterclockwise limit. And I got it right in that diagram, thankfully. And we actually set it up for resistance measurement. So that this is the circuit that is used for resistance measurement, which we skipped. But it's in the electrical measurements chapter. And then we do ohm meter measurements of the potentiometer, looking at the resistance between two of the terminals, the one in the lower right, and then the middle terminal called the wiper terminal. And as we take the different measurements, in terms of kilo ohms, it goes from 0 to 10 kilo ohms. And that is because there's this long resistive element here. And what the wiper inside the underneath the potentiometer knob does is it touches that long resistive element at a certain spot. And then that resistance can be measured. So if you probe it at wiper and at B, you get this amount of resistance right here. And then, so that's some portion of 10 kilo ohm. And then the remainder of that 10 kilo ohm is measured all the way across here between A and W. And so the students spend some time getting familiar with that, with taking the ohm meter measurements on the, and then here's a real world application. Each joystick usually has 2 potentiometers inside it, one for one axis and then the other for the other axis. And so it's what gives game controllers information about how what direction you've pressed the joystick into. Okay, then we also do voltage measurements. So that was with no power connected. Then we add some power to the A and B terminals, these terminals on the right here, and then we measure the voltage between the B terminal and the wiper terminal. And in doing that, what we end up seeing is a voltage that corresponds, that increases as we turn it from its counterclockwise limit over here to its clockwise limit. As we do that, we see the voltage increase. And so students go through all this and they get to know the potentiometer in a great deal of detail. But again, in 4.5 hours, there's only so much we can go through unless you put me on fast forward. And then another fun thing is to use the Cyberscope to graph the voltage. And let's see, where is the script for that? Here it is. Okay, so I'll paste this into, or I'll show you how to open it first. So what I'm going to do is paste you a link. And when you follow the link, it's going to open to a, because this is unpublished stuff we're going through right now, this is going to open into a download page, and you can just hit download and that'll download the script for you. Copy, then paste into the chat. Okay, so remember, you'll go ahead and click the link, follow it, and then when you get to the download page, hit the download button in the center. And then going back, we'll need to look at the, do I not have the electrical connections for that? Okay, I'll go ahead and put the electrical connections for the probes onto the screen. Okay, so for this one, we're going to, oh, I know where it is, sorry. Let's see here. Oh, okay, here we go. So wiper terminal, row 29 for your red probe. And then of course on P2 for the other end. And then row 30 for your black probe. And then that goes to the P0 clip. So, so go ahead and add that.
Andy, when we download the hex file, how do we get that into our microbit?
Okay, so the question is, once you've downloaded the hex file, how do you get it into your microbit? And it usually appears at the bottom of your browser, and you can drag and drop it into your editor.
Okay, thank you.
Yes. So for me, I did it into a different browser. So what I need to do is open up my file browser. That's Finder in Mac, or forget what it's called in Windows. It used to be Windows Explorer. Now it's folders, something like that. So I'd go to my downloads and then find plot P4 volts with Cyberscope and drag it into the drag and drop it onto the python.microbit.org editor, then flash, then disconnect, then go to Cyberscope and click connect. Select your microbit, connect, and then you'll get a line going across the Cyberscope screen. And as you rotate the potentiometer, you will see that line go up and down, except for that I didn't connect my stuff like I had in the picture. So black probe to 3-pin header on P30, and then to row 30 by the potentiometer. Red probe to P2. Black probe was P0 to row 30. Red probe is P2. And then you can actually go into the P4 socket with the red probe, or you can go right on row 29 like that. Right by the wiper. Go ahead and zoom in on that.
We have about 10 minutes.
Thank you. Okay. So the black probe goes right on the B terminal. That's the lower right terminal of the potentiometer. And then the red probe goes on the W or wiper terminal. And that's row 29 on the left side of the potentiometer. Once you've done that, you can rotate the potentiometer knob back and forth, and you can see the voltage measurements graphed between 3 volts and 0 volts. And the students have a lot of fun with this, and it kind of gives them a hands-on feeling for how an oscilloscope is really just a device that plots measured voltages over time. And they really get to have a hands-on experience with that.
Just a comment from Julie. I'm having so much fun with this.
Oh, thank you, Julie. I'm really glad to hear that. I'm going to do one last demo before talking about the teacher resources, and it should go quickly. And this one, you can go ahead and try yourself later, but because we're limited on time, I have to just show it to you as opposed to have everybody do it. And it's what we're doing here is we're using an oscilloscope to measure both the signal that's going to the servo and the signal that's going to the potentiometer. And so the first thing I have to do is put the red probe on the P16 pin where the potentiometer is going. And then I'll put the black probe on the servo's wiper. And then load that script, which is called plot P4 volts with Cyberscope. I apologize. Potentiometer controlled servo. I was in the wrong spot. Measure. Okay. Measure signals, potentiometer and servo signal. Now I'm finally in the right spot. Here is the correct script. Download. All right. So when you're using the Cyberscope, you can click connect and then flash, but you got to make sure to disconnect. Otherwise the Cyberscope might get kind of funny. So when the first thing you see is just kind of the left side of the Cyberscope is turning red. But if you take the time per division, so right now it's 10 seconds or 10,000 milliseconds for that. That's the total across the screen. And if we go down to say 20 milliseconds, then we can see the actual servo signal. And I'm going to decrease the y-axis a little bit too. And if you zoom in even further on time, like now every one of these squares is only 5 milliseconds wide, you can see the servo signal, but it's kind of hard to see. And so there's lessons in the text that show how to use a trigger, which causes some crosshairs to appear on the Cyberscope. And then the rising edge of the trigger here lines up with the vertical crosshair. Like I'm going to move this trigger, the vertical trigger, back to from 10 to 5. And as you can see, the signal that we're measuring and these little square pulses here are the servo pulses. And then the line going across is the potentiometer. And as I twist the potentiometer, you can hopefully see that the line, the level of the potentiometer dropped, but also the width of these pulses here got narrower. And it's because the amount of time that the pulses stay high, which would be equivalent to a light on, is what actually controls the servo's position. So what we're measuring both the potentiometer and the servo signal, which is coming through very rapidly at 50 times a second, just like with the LED brightness. And so I just moved the potentiometer all the way to its clockwise limit. And now these pulses are wider. And so this is a way of showing students how to use some more sophisticated oscilloscope measurement techniques. And you can even zoom in on the time even further. Like if you go down to 1 millisecond, you can actually pretty much rough estimate how long that pulse stays high to give the servo that particular position. And then, okay, so I'm going to turn the potentiometer to the middle, and the wideness of the pulse reduced. And the more I turn it, the narrower the pulse becomes, and then that potentiometer voltage goes down low. So that's one of the upcoming lessons in the potentiometer position sensing. And you'll get to go through those much more step by step. I just wanted you to try a few of the things like measuring the potentiometer. Well, the previous example we did. Okay, so on to a few last things. www.parallax.com is where you can go shopping. If you want to go shopping for microbit things, there's a category microbit. I'll paste that in. And then if we go to that page, there are even options for kits. And then here we can see the What's a Microcontroller, the 12 pack of the What's a Microcontroller kit. And then further down, here's the individual What's a Microcontroller kit that we sent you. So this link is where to find the various kits if you're interested in getting some for your class. A reminder that learn.parallax.com is where the student resources are up front, but it is also where the educator's resources are. So I'm going to skip ahead just a little bit. So this here is learn.parallax.com and then the educators tab. So now I'm at learn.parallax.com. When I click the educators tab, if I'm logged in as a teacher, it looks roughly the same. I'm not logged in yet. And so here are the What's a Microcontroller with Python and the microbit teacher resources. And there are some things that are not hidden away. And for example, there are teaching strategy guides that you can view as a PDF because there aren't any answered student questions in this. So we have it publicly facing, and it just includes some ideas for implementing it. And then there's also some advice on grading. And Stephanie, I don't know why, but it looks like there's, oh, activity bot scope and sequence. I don't know why that's there. Then there's the locked off area. And in order to get to the teacher's resources, you need to log in using the password that made it. Okay, and now if we go back to What's a Microcontroller with Python and the microbit, instead of that lock icon image, we get to the teacher downloads. And so here they all are. And so we could take a look at one of the zips. I guess we'll do LED lights since I happen to be pointing at it. Okay, so I just double click the zip to extract it. And then we have 3 different versions of the same teacher's document. And so the first one is, so this is a solved worksheet that has some matching and basically it's some student worksheet type things. And then the solutions come afterwards. There's also a test bank for the LED chapter. And this is the same pattern for every chapter. Where did the test bank go? Okay, it looks like that is just a Word document. And I think a weak point in my plan was oh, okay. What's happening is that I have a Windows virtual machine on this Mac, and it's going to open that in Windows. So I can't show you the test bank, but what I can do is explain that it's essentially a second set of what the students see inside each of the chapters. So if we're in LEDs, each of the activities, these guys, like if we do intro to lists, at the end of the activity, there's review and practice, and there's questions, exercises, and projects. And for the students to practice, we also have solutions. I'm going to try a different one because I'm not seeing the solutions here. I'll go into electrical measurements. And so here's the review and I don't know why the solutions are missing from that page, but we'll see if we can find them and make sure they're posted. So normally questions and exercises and projects would look something like this. And then there are a set of solutions in the actual student material. And what that zip was that I couldn't open because I forgot about Microsoft Word and my Mac here, is that there's a similar set, oftentimes asking the inverse of whatever question the students see in here, or a related exercise or a similar kind of project, so that they've had practice and they could do it in a quiz or an exam, or homework, regardless. This is where the students get to try it. And then there's a second set that's available for download that the teachers can try, or that the teachers can have to assign as quizzes, exams, homework, however they want to do it. And they're all solved. Cyber.org. I'll paste this link into you. They have microbit curricula, cybersecurity. They have some network lessons. They have quite a variety of different curricula that they share with teachers in the United States. And all you have to do to get access to their curricula is to sign up. The sign up link is right by login. And since we're a little over time, I'm going to skip that demo. Just wanted to let you know that that's an additional resource for programming the microbit with Python, for example, in addition to some of the other ones we talked about earlier. Another thing that the microbit is used in is the Cyberbot robot. The Cyberbot robot is another way of giving kind of a physical manifestation of the code you write. And here's an example of a lesson where the code tells the robot to go forward and then make a right turn. And then by simply expanding the code, by nesting that forward and right into a loop, into a for loop that repeats 4 times, that forward and right turn becomes the maneuvers to draw a square with the robot. And that's kind of a neat thing. The Cyberbot has, and then there's a lot of different things you can do with the Cyberbot. Like here's an example where it's got some whiskers attached to it. And here's an example of a light sensor. I think if I wait long enough, it will start. So there it goes, bumping into the box, bumping into the wall, and then on its merry way. So there's similar videos for light sensing and for infrared, which is non-contact, but like whiskers, where it detects an object and can either follow or avoid it. And then with the microbit built-in radios, there's kind of a fun demo here where there's one microbit that's connected to the computer and it's radio broadcasting speed and distance commands that are typed into the computer. So it goes out the microbit connected to the computer and then into the radios on each of the robots. And so you could have potentially a whole class full of robots doing coordinated maneuvers. So those are some fun things. And then last up is how to get help. We have an educator hotline that is open. Is that right? Yeah, it's open 8 hours a day. I believe it's from 8 to 5 Pacific time. And then we have education@parallax.com. That's an email that goes to a group, and whoever is most suited to answer the question will pick up your email and call you. Sales has an email and a phone number. There's also a discussion forum, and we're on Facebook. Cyber.org, which supported this effort, would like to thank you for watching. And we at Parallax would also like to thank you for watching and participating and trying out the activities. And I very much encourage you to go back now that you've got your hands into these projects a little bit and follow them in a more step-by-step fashion. There's a lot to learn there, and there's a lot of material to cover.
Andy, did I miss it, or did you point out the upcoming cybersecurity course?
You missed it. Thank you for the reminder.
I did?
No.
Okay.
I missed it. Gosh, I'm just
Okay.
in fine form today. I don't know it must be Friday.
I commend all of you for staying or for coming in the first place on a Friday evening. We appreciate it.
Yes, we do greatly. So this is the chaos that it looks like when I'm presenting. And we have 4 workshops coming up. The first one is cybersecurity in late July, 25th, 27th, and 29th at 3 p.m. And so this is a workshop where you'll get to try radio communication, and you'll get to see how that can be monitored inadvertently, and then how to prevent that kind of radio communication from being monitored.
I've posted a link to that course as enrollment is open on that one, as is a Cyberbot course.
And then there's an upcoming Cyberbot course, and you get a Cyberbot to do the hands-on workshop of that course if robotics seems like it would be another thing that would work in your classrooms. Then there's the activity bot. This is programmed in Blockly. It's also programmed in standard C language, but the workshop focuses on Blockly. And the neat thing about this robot is that the microcontroller is multi-core. And so you can actually take parts of your program and have different cores execute them. So you might have one core that's controlling the wheels, and then a separate core that's checking to see if there's an object in front of it with infrared detectors. And this one you know about. So if you have colleagues that you think might be interested in it, in this course, let them know. Also, if you feel like just getting a refresher on it, hold on to your kit and just let us know that you want to sit in, and we can have you attend, as well as the folks who sign up and receive the kits to do the hands-on stuff. Thank you for the reminder, Stephanie.
You're welcome.
Yeah. Andy, Stephanie, Ari, great course. Got a question about the use of Python. So Python's only involved with 3 of those workshops, right? The Cyberbot, the one you just mentioned about the security.
Yeah,
and also
cybersecurity,
this course.
Cyberbot, and then this.
Okay,
Yes.
great.
And then this one is Blockly. And we'll probably take a quick look at some C language examples. Blockly generates C language, and so you can, in the Blockly editor, see both the C language and the blocks.
Should I stop recording in case anyone needs final help with troubleshooting anything?
Yes, that would be great.
Okay.
Thanks for coming, everyone.